This is the third of 4 parts on the psychology of reasoning. In this part, we'll talk about deductive logic. We saw in the last section on reasoning that reasoning is not an innate property of the brain. Children's reasoning is full of contradictions and non sequiturs. This led Piaget to realize that the elements of reasoning must appear over development, and specifically to conclude that the elements of reasoning appear over a great many years. Now, one of the first elements of reasoning to emerge, we saw, was the formation of basic level concepts in infancy. Concepts like dog or cat. And we also saw that these basic level concepts are heavily influenced by the statistical properties of the perceptible features, what we called Q validity. This is one of the reasons that basic level concepts are formed first. It's also heavily influenced by what children pay attention to. If the property has high Q validity, but children don't notice it, like the wick on a candle, then it doesn't play a large role in their reasoning. And then last, basic level concepts are also heavily influenced by how children think that the features are related to one another. If I told you that I have an animal and that it doesn't fly and it doesn't have wings and it doesn't build nests in trees, but it has bird DNA, you'd probably say that it's likely to be a bird, because you know that in all the other birds, bird DNA does cause wings and does cause the bird to fly and does cause the animal to at least be able to build nests in trees. So what we've seen is that early on, one of the first elements of reasoning to emerge are concepts. And children are already beginning to combine concepts with the other elements of reasoning in the first 2 years of life. So as early as 2 years, children are integrating concepts, relations, and quantifiers into propositions. And you'll hear them say things like lions have manes, or only people can move, or boys don't have eyelashes. Now, some of these propositions might be wrong, all right, but children are forming them. Children's propositions, though, are different from adults in a few ways. They're not perfect. Their concepts are often not scientifically correct, so they might think that all living things move, but they might not realize that plants are living things. They tend to be stuck at the basic level, so they might be reasoning about flowers, but not up to the level of all plants. And reason, so if they hear that plants need water, they might not realize that that applies to flowers. They also often omit quantifiers. So children will say lions have manes, but they don't specify that all lions have manes versus most lions have manes. That's an important difference. If most lions have manes and you find out that Leo is a lion, it's a good chance that Leo has a mane, but it isn't certain that Leo has a mane. But do they combine then these propositions logically? Piaget thought not. Piaget thought that even when they're at the stage where they have these concepts, relations, and quantifiers such that they can say things like lions have manes, they're not yet representing those as a logical proposition. And his reasoning for this came from a very basic kind of analysis that he did. So all of logic depends on what's known as the law of identity, that A is A. This is what gives rise to the law of non-contradiction. If A is A, then A is not A. And therefore, you have to avoid contradictions in order to preserve the truth that A is A. This has another implication, which is that if you have A and you don't add anything to it, it's still A. And if you have A and you don't take anything away from it, it's still A. A is A. And that kind of thinking, Piaget thought, was way outside the capacity of preschoolers, that they were effectively logic blind, or what he called pre-operational, until they were able to do this with at least concrete objects. And his reasoning for thinking that the child doesn't understand that A is A came from a famous set of studies he did on children's ability to, as he put it, conserve quantities. Hopefully this video will show you this.
Are they the same? Okay, so now watch what I'm going to do. Okay, now. Which has more water? This class, or they're both the same? They're not the same. Which has more? Why does it have more?
Bigger.
There you go, because it's more bigger. Now this is an interesting one. We had two glasses, A and another glass, which was equal to the first glass. So A is equal to A. She didn't add any water, and she didn't take any water away. And yet here the child says that given this transformation, there's more because it's bigger. It's as if she doesn't realize that the quantity of water has been conserved over its transformation, that A plus 0 equals A, and that A minus 0 equals A. Now, you might think that part of the problem here is that a continuous quantity like water is maybe difficult to track. After all, you can't count the amount of water. So Piaget gave a different kind of problem. This one seemingly much easier. This is a number conservation problem.
Tell me, are there more red chips, or are there more white chips, or are there the same number of chips? They're the same. Now, I can't watch this. Okay, now tell me, are there more red chips, are there more white chips, or are they both the same? They're not the same? Which is more, the red chips or the white chips? And why are there more white chips? How do you know there are more white chips?
Because they're apart.
So what's interesting about this is that this child is actually old enough to be able to count the chips. And that's not what she does. She sees that A, the red chips, is equal to the number of white chips, also then equal to A. The two quantities are the same. You didn't add any chips, you didn't subtract any chips, and yet she says that the chips, when they're all apart, is not equal to A. So that's Piaget's explanation for what's going on here. Is the child's effectively logic blind. The child doesn't understand that A is A. Well, that idea was enormously influential up until about the late 1960s, early 70s, when evidence started to emerge that Piaget was really only showing us a tiny part of the child's thinking. So one problem with Piaget's idea that you go from this pre-operational logic blind stage, where you can't solve a conservation problem, to a concrete operational stage where you are able to solve conservation problems in the concrete operational stage, came from an experiment by Meller and Bever in 1968 that was published in Science magazine. Here what they did is they gave children these three types of problems shown in panels A, B, and C. Panel A is very easy. Just have to establish that the child is capable of one-to-one correspondence between the experimenter's row on top and the child's row down in the bottom. Everybody can do that. The other is a situation where you put the number in conflict with the length in B and C. In B, the item that is more dense has more objects, and in item C, the object that is less dense has more objects. Now, the key thing that Meller and Bever did is they gave two different versions of A, B, and C. In one version, they're just clay pellets, but in the other version, they're M&Ms. And children get to eat the one that has more M&Ms. So now children are pretty motivated to give you the row that has more. What he found was pretty interesting. On the problems like B and C, when the items were clay pellets, if you look at the x-axis, the smallest bar there, the one where you have the fewest number of kids showing conservation, is happening when kids are 3 years, 8 months to 3 years, 11 months. And it gets higher for 4 years old to 4 years, 3 months, and still higher at 4 years, 4 months to 4 years, 7 months. So that shows the part that Piaget was showing in his experiments, going from non-conservation to conservation. But they went longer. They looked at what happens when children are still younger than 3 years, 8 months, all the way back to when kids are in their 2s and early 3s. And here you're finding that almost 100% of kids are solving the conservation problems correctly. So first they're almost perfect, then they go down in performance, and then they rise again. That's not at all like the kind of stages that Piaget was describing. The other thing that they found is that on the M&M's version of the task, where kids got to eat the largest number of items, children between the ages of 2 and 4 were equivalently successful and at a high level of success. Well, what you'd expect from chance, being between about 60% and 80% of the time. So again, that's not consistent with the idea of a pre-operational stage to a concrete operational stage. It's not stage-like because they don't have just one way of thinking, pre-operational to concrete operational. And the other thing is that we've got this weird U-shaped development happening on the clay problems, but not the M&M problems. What people thought is, maybe what's happening here is children know that A is A. They know that when they're about 2 years old. All right. But they're learning something else that's interfering with their performance by the time that they're 3.5. And then whatever it is that they learn, they make an exception to when they're, say, 4.5. That's somewhat what we saw in the development of the past tense, where children initially say, I went to the store, then they learn something new, like you make the past tense by adding ed, and then they say, I go to the store, and then they realize, oh no, it's not I go to the store, I was right before, I went to the store. We're seeing something similar like that with the clay pellet problem. But what is exactly that the children are learning? Well, one idea is that what children are learning is that when the experimenter transforms the set, the child might think, they're transforming the set to help me out. And since they're trying to help me out, I need to change my answer to sort of go along with what the experimenter is doing. Well, if that's right, then if you were to change the experimenter so that the person who's doing the transformation isn't a helpful adult, but instead is somebody who's maybe naughty, then maybe they wouldn't fall into this trap. Well, to test this idea, McGarrigle and Donaldson gave children the conservation problem, but this time, instead of the experimenter rearranging the chips, it was Naughty Teddy. And they'd say, oh, look, it's Naughty Teddy. He's going to spoil the game. Right? And when they did that, even the 4 and 5-year-olds performed as well as the 2-year-olds and the 7-year-olds. So it seems like we have a way of integrating these findings. All right. So the M&M's condition shows that children do understand that A is A. All right. And in the clay pellets condition, something more complicated happens. Younger children succeed in the conservation task and are not fooled by the transformation. Older children fail because they wrongly think that the experimenter is trying to help them. But if older children know the transformation is ill-intended, like because it's being done by Naughty Teddy, right, then they can serve just as well as younger children. But overall, it seems that children's default understanding is that A is A. Now, if kids understand that A is A, then they should be able to reason deductively. They should be able to reason deductively. Now, deduction is reasoning from the general to the specific. You might know a general fact, like all objects exist in an ordered series. If this is right, all right, then you can engage in a transitive inference or engage in transitive reasoning, like if B is greater than A and C is greater than B, then C must be greater than A. We also see deduction in syllogistic reasoning. The very first example I gave you, all men are mortal, Socrates is a man, therefore Socrates is mortal, is a syllogistic deduction. Well, how well do people do on these problems? Can children solve these deductive reasoning problems? Well, if we look at transitive inference, we find that young children who are who Piaget would have classified as pre-operational are capable of engaging in transitive inference. So Bryant and Trabasso would teach children about a series of rods that were hidden in a block. So you couldn't see anything but the top of the rods. And you had to remember, all right, how long each of the rods were. So A would be shorter than B would be shorter than C would be shorter than D would be shorter than E. And they were just trained to 100% accuracy on those pairwise comparisons, A to B, B to C, C to D, and D to E. Right? They were never trained on other comparisons, like which is greater, B or D. Right? In order to answer a problem like that, they had to rely on transitive inference. And they found that nearly 100% of subjects were performing at above chance levels. We also engage in transitive inference using verbal tasks. Here, children aren't quite as well as in the nonverbal versions. A verbal version would go something like this. Billy is funnier than Sinbad. Whoopi is funnier than Billy. Is Whoopi funnier than Sinbad? Well, yes, if Whoopi is funnier than Billy and Billy is funnier than Sinbad, then Whoopi must be funnier than Sinbad. Now, how do we solve a problem like this? Well, it seems that these kinds of series problems are solved by representing the concepts as positions on a mental number line. So if you can imagine that we have a kind of mental number line that represents how funny the individuals are. All right, when we hear that Whoopi is funnier than Billy, we might put Whoopi to the right and Billy to the left of Whoopi. And when we find out that Billy is funnier than Sinbad, we put Billy to the right of Sinbad. And now when we're given a problem, who's funnier, Whoopi or Sinbad, we can simply visualize their positions and see that Whoopi falls further to the right than Sinbad, and therefore know that Whoopi is funnier than Sinbad. And the evidence that this is the way that people seem to reason comes from a quirk of transitive inference. And that is that as the distance between any 2 points increases, the speed and accuracy also increase. So if you have a series like A, B, C, D, E, and F, and you're asked about 2 points that are very far apart, like B versus E, all right, you'll be super fast and accurate. If you're asked about ones that are a little bit closer together, like B versus D, then you're not so fast and accurate. And if you're asked about an adjacent pair, like B versus C, you'll be the least accurate. This is the same thing that you would see on perceptual judgments of line length. In fact, it's also subject to Fechner's law. So it seems that we're solving these serious problems by representing themselves to ourselves, as something like lengths of a line, where everyone is a different length on the line. Right. Now, in addition to this, there's something like the mental number line that maybe is involved in syllogisms. All right. Now, syllogisms are something that young children have much greater difficulty with in comparison to transitive inference. They're pretty good at transitive inference, but at the same time that they're good at transitive inference, they might be bad at syllogisms. And to understand why they would have difficulty with a problem like all men are mortal, Socrates is a man, therefore Socrates is mortal, we have to look at how adults, who normally aren't trained in logic, solve syllogisms. And the theory that seems to work out best for how it is that adults solve syllogisms is what's known as the mental models theory. All right, so let's take an example like all chefs are violinists, and Mary is a chef. Is Mary a violinist? How might you solve that? Well, according to the mental models theory, what you do is you visualize a series of chefs and a series of non-chefs and a series of violinists and a series of non-violinists that conform to the rule that you were given. So in the same way that the transitive inference problem are solved by visualizing items on a mental number line, syllogisms might be solved by visualization. So the idea would be, let's suppose you have a major premise like all chefs are violinists. That's what's shown here. All the chefs are violinists. Minor premise, Chris is a chef. Is Chris a violinist? Well, now you just look at your mental model and you see, well, all the chefs are violinists. If Chris is a chef, then he must be a violinist. Now we have another problem. Let's suppose that we know that Chris is not a chef. Is Chris a violinist? Well, now we look at all the people who aren't chefs, including this guy, and we say, is Chris a violinist? And the answer is, I don't know. Maybe he is, maybe he isn't. That's deductively correct. Now let's suppose that we know that Chris is not a violinist. He's one of these three people. All right. Is Chris a chef? And the answer is no. Now, what's interesting is that when people are given, say, a visual depiction like I've shown you, these problems are really easy. When people are given the problems and they have to solve it on their own, they seem to create these. And why do we think that they're creating them? Well, one is that problems that are hard to visualize are also hard for adults who aren't trained in logic to solve. So a problem like all chefs are humans, that's easy to visualize. All chefs are violinists is a bit harder to visualize. All BIM jams are quillagogs. That's very hard to visualize. I don't even know what a BIM jam or a quillagog looks like. I could make it up, but that's going to take more effort. This explains why adults are able to solve abstract, hard to visualize problems more easily than easy to visualize problems. It also explains why adults are able to solve abstract, hard to visualize problems better than children. And it also explains why children can solve transitive inference problems more easily than syllogisms, because visualizing points on a line is easier than visualizing complicated sets. Now, I said that this is true of people who aren't trained in logic, and that's true. But I should notice that even logicians resort to visualization. In fact, if you've ever taken a class on logic, they often try to teach you what's known as predicate calculus. That's what's shown on the top half of this figure. This is a predicate calculus representation of all men are mortal, Socrates is a man, therefore Socrates is mortal. It's known by the technical term the modus barbara. But to understand it, what logicians often do is they use Venn diagrams. And what Venn diagrams are beautiful visualizations of the distribution of properties that are being discussed in the argument. So this seems to be a pretty universal feature of syllogistic reasoning and how it is that we're able to engage in it. Now, in the next class, we'll look beyond deduction and we'll look at induction.